guys, welcome back to my channel again. Today we're going to continue the journey on quarks. Now we have something called fermion. What is a fermion? I have to write this because something like this might be very strange to you. When I'm saying fermion, you must be wondering, what is this? What's up? What is fermion? But if you have been following me, you must have an idea about quarks. I've been talking about quarks. Sorry, I'm just trying to clean this. And what I'm talking about is something written. I can give it like this. We are dealing with particle physics, and there is something called fermion. You can see that. Yeah. Now, there's a noun of it like fermion, the way it's pronounced, that's not important. A particle such as an electron, proton, or neutron, right, is what we call a fermion. Now, whose spin, quantum number, I've told you time and again what is quantum. Tiniest particle, very tiny states, phenomena, quantum nature of something, whose spin, quantum number, is an odd multiple of a half. Compare boson. Now, a fermion is any particle that has an odd half integer. It has an odd half integer. Now, I've written this, so below that I'm going to write this. It has an odd. You know what's an odd number? Even number and odd. If you have done some maths, you must be knowing what odd is and even is. Divisible by 2, not divisible by 2. So it has an odd half integer. A fermion is any particle that has an odd half integer. Like, for example, 1/2, right? And 3/2, and so forth. Spin, quarks and leptons, as well as most composite particles like protons and neutrons, are fermions. So a fermion is any particle that has an odd half integer spin. And in this group we have quarks, leptons, as well as composite particles like protons, neutrons. These are all fermions. Now let's go further. What is a fermion or boson? I'm going to write these terminologies as we go by, so that because you might not get the English pronounce words. We're talking of boson, this. So the question is, what is a fermion? I've told you what a fermion is. Now there's a new word here, boson. Now, fermions are particles which have an half integer spin. I've told you that, and therefore are constrained by the Pauli exclusion principle. Particles with integer spin are called bosons. Particles with integer spin are called boson. Okay. What is an integer? Integer is a whole number, like 1 is an integer. So if you write a half, that's be a half integer. Okay. So fermions include electron, protons, and neutrons. Protons, this is what makes up an atom. So fermions include these three: electron, protons, and neutrons. So the word you are given, fermion, should not confuse you. It refers to these things. This part. You could call them particles actually. Their particles integer spin are called boson. Fermions include electron, proton, and neutrons. Now, before we proceed, I'd like to tell you what Pauli exclusion principle is. For those who have done doing particle physics, you know what this is. Now, in quantum mechanics, right? You know what's quantum mechanics? I've been talking this in the previous videos if you have watched. The Pauli exclusion principle states that two or more identical particles with a half integer spins cannot occupy the same quantum state within a quantum system simultaneously. Okay, get it? So let's see what that means. So here we have, for example, what this thing is talking about, and there we have something like this. This is a first, this is a second, blah blah blah, two particles, whatever, and then we have another state. I'm gonna show you. Don't worry, just be happy. We're gonna make particle physics very simple for you to follow, and even you're gonna like it actually. First, second, and it's quite interesting if you develop the curiosity to learn. Now, this does not exist, and do you know the reason why? Because if you look at these two, they occupy the same quantum state. And these are opposite, but these are not. So this is really agreed. These both are going opposite each other. This is correct. No, this is not. This is correct. Okay, I've ticked it. It's correct. So this is Pauli exclusion principle. What it says, which I've just read to you. Let me take water, guys. I told you we're going deep down. Now we are actually dealing with quarks, and even below the quarks. I don't think we are below. We are in the quarks because we're talking about fermions, and I told you what fermions are. Because it's any particle that has an odd half integer spin. Quarks and leptons, as well as most composite particles like protons and neutrons, are fermions. So quarks are included in this. So let's proceed. We're having a class, a really particle physics class. What is the size of a quark? You see, I told you I'll ask you questions and answer them. So you watch as I answer these questions. What is the size of a quark? While the size of protons and neutrons is of the order of a Fermi. Now I'm gonna write it. I'm gonna write it. This is really a class that we're having. It has a Fermi in the order of 10 raised to minus 15 m. Okay, m stands for something maybe momentum. Now this is a unit. This is what while the size of proton and neutrons is of the order of this. So this is proton and neutrons. This is how small they are. 10 raised to minus 15. The size of quark is, now quarks will be, the size of quarks will be 10 raised to power minus 18 m. Okay, it is, I don't know whether you are seeing, sorry, because I'm looking at the notes at the same time I'm showing you. Also sometimes I'm showing you like this. Here, this is a quark, and that's a Fermi, which includes all types like neutron, protons, quark and stuff, fermions. Now, it is deemed that quarks are composed of smaller particles, preons. They are called preons. Smaller particles called preons. You can be taking notes as I'm showing you this, called prions. Now we're gonna draw a rough idea. You know, these things we just draw them to illustrate what we understand about them. So I wanna draw something called a quark. So just like this, and then so like this, just simple like this, and like this. I'm gonna show you in just a second. This is a quark. I'm doing pretty fast. 2 up quarks and 1 down quark. This is a proton. You can see this 2 up quarks. While I explain that. Now, while we did about that, now there are 2 up quarks and 1 down quark, owing to a phenomenon known as color confinement. I just gave you a drawing of this should be a proton, 2 up quarks and 1 down quark, and a neutron, I think it has 1 up quark and 2 down quarks. Yeah, and this is actually positive and this is negative, so this weighs more than this. Yeah, and so I think that's why a neutron weighs more, because it has 2 of these and 1 of that. So let's go on. Owing to a phenomenon known as color confinement, quarks are never found in isolation, right? They can be found only within hadrons. I told you what an hadron is, so I'm not going to repeat it. If you don't know, you go back to the video and find out what hadrons are, which include baryons such as protons and neutrons, and mesons, or in quark, gluon, plasma. For this reason, much of what is known about quarks has been drawn from observation of hadrons. Let me try to see whether I can get this pretty fast, really quick. I don't know where we did this. We have had quite a range of things. Well, if I'm lucky, or you are lucky, I'm gonna tell you what this is. But I don't. Luck doesn't seem to be on our way, because we've done pretty much a lot of things. I'm trying to find out something which you've just done. I don't know where I've defined this thing. Oh man, where is this? Well, you go back on my videos and you'll find out what an hadron is. And yeah guys, so let's proceed with the video. And where we are right now is now I've shown you what a quark looks like, and now I don't know whether you can see it here. If I give it close, this 2 up quark and 1 down quark. This is a proton. Now a proton is composed of 2 up quarks, 1 down quark, and the gluons that mediate the forces binding them together. So it has 2 up quarks, 1 down quark, and the gluons which mediates the forces which binds this thing together. The color assignment of individual quark is arbitrary, right? But all the 3 colors must be present. Red, blue, and green are used as an analogy. Just it's used as an analogy, which means they don't really exist, but we are using these colors in order to illustrate a point. It's used as an analogy to the primary colors that together produce a white color. This is about quarks, right? Now we're going to composition and the elementary particle. So we have statistics, fermionics, generation, first, second and third, interaction, strong, weak, electromagnetic, and gravitational. We have those four forces. We have gravitational, electromagnetic, strong force and weak force. Okay, now the symbol for is Q, that's for quark. Actually, surely we're talking about quarks here, right? And antiparticle or anti-quark, or maybe I have to write it, but you know the spelling already. I'll show you something like this. Symbol is given like this, and the antiparticle symbol is given like this with a bar above. Anti-quark, sorry. Antiparticle, anti-quark. Theorized by Murray, Gell, Mann, 1964, George Zweng, ZWEIG, 1964. Now discovered by Slack, 1960, quite a long time ago actually. This is something which was discovered almost half a century ago. You see, people have not been idle. It didn't start today, it's an old thing. Types, we have 6 up. We have 6. Now we have up, down, strange, charm, bottom and top quarks. The names we give them so that we can be able to explain these things, but they're actually same things, going slightly more than the other or behaving with some properties not the same. And we have electric charge, which is positive 2/3 elect E, or -1/3 E. That's electric charge. Column charges, yes, they have color charge. Spin, I have integer spin, I've told you, and barons is 1/3. Now quarks have various intrinsic properties, including electric charge, I'm explaining, mass, color charge, and spin. They are the only elementary particles in the standard model of particle physics to experience all 4 fundamental interactions, right? Also known as fundamental forces, which is electromagnetism, gravitational, strong interaction, and weak interaction. Now, as well as the only known particle whose electric charges are not integer multiples of the elementary charge. Now, there are 6 types known as flavors of quarks: up, down, charm, strange, and top, and bottom. So those are the 6. Up, count them: up, down, charm, strange, top, bottom. Now, up and down quarks have the lowest masses of all the quarks. Okay, they have the lowest masses, which I've just shown you before, which makes up a proton. We have 12 quarks and 1 down quark. Okay, the heavier quarks rapidly change into up and down quarks through a process of particle decay. If they are heavier, they change, means they give up radiation and come down to this stable state in nature. You know, in nature, something moves from higher energy state to a lower energy stable state. So this is what is happening here. The transformation from a higher mass to a lower mass state. Yeah, actually it's talking about that particle decay, which is a transformation from higher mass state to a lower mass state. Because of these, up and down quarks are generally stable and the most common in the universe. Because of this, up and down quarks are the most common in the universe we live in. Whereas strange, charm, bottom, and top quarks can only be produced in a high energy collision, such as those involving cosmic rays and in particle accelerators like in the hadron. in the Switzerlands, right? You must be aware about hadron colliders in CERN. This is where you find these things are produced. For every quark flavor, there is a corresponding type of antiparticle known as antiquark that differ from the quark only in that some of its properties, such as the electric charge, have equal magnitude but opposite sign. So they are basically the same, but the signs is flipped. So when it's positive, the anti of that, because it's just normal maths, you know, the opposite of plus is minus, so it's just a flip. So the antiparticle differ in the sense that it has a negative sign. So, but it's equal magnitude. So the quarks model was independently proposed by physicist Murray Gell-Mann, and I've told you about those people who discovered them. Quarks were introduced as part of an ordinary scheme for hadrons, and there was little evidence for their physical existence. There was little evidence for their physical existence until deep inelastic scattering experiments at the Stanford Linear Accelerator Center in 1968. The accelerator program experiments provided evidence of all 6 flavors. The top quark first observed at Fermion in 1995 was the last to be discovered. Okay, so yeah, we really fit physics here. Now we're gonna look down what really are these quarks, which are the fundamental what do you call it, unit of matter, you know, not unit, particle of matter. Fundamental means they're really deep down. So quarks makes up so many of these things that we are made of, and we've gone down with quarks. Now, what are fermions? I've told you what fermions are. What are half integer spin? Because I've been talking about half integer spin, like these electrons, neutrons, protons, quarks. You know, they have half integers. What is a half integer spin actually? Complete, like boson has just a complete spin, but these others have half integer spin. So half integer spin fermions are constrained by Pauli exclusion, which I showed you before, whereas integer spin boson are not. The electron is a fermion with the electron spin over half 1/2. Okay, so electron is a fermion. I told you is a fermion. And these 3 things make up an atom, by the way. You know, electron, proton, and neutron make up an electron, and they have integer spin. Okay. Half integer spin means if you take them from their position throughout the rotation, they'll go to where they'll stop after making a complete rotation will be a minus. Yeah. But in a whole integer spin like a boson, it will be 1. That's the difference. So they have to go twice in order to come to the original position. That means 720 rotation twice in a circle. That's why these things use the half integer spin. So if you take them from the original position, rotate them around where they stop at the negative sign, not from where they started. So you have to take them around again, then they'll come to where they started from. Okay. Now the electron spin, I've told you. The quarks are also fermions. I have told you that with spin of half. Okay. The photon is a boson with a spin 1 photon, light. Light is a photon. I mean, it gives a photon. Sorry, I think the camera is not lying properly here. Right? So it has a complete one spin, which is a typical boson spin. Light photon was the quanta of electron. Electron is a photon, right? A quanta of electron is a photon. You can correct me if I'm wrong. What is a half integer spin? I've told you that in general, particles with a half integer spin are called fermions. In general, particles with a half integer spin are called fermions. By half integer spin, we mean values like 1 over 2, 3 over 2, 5 over 2, etc. Although it is not known if there exist particles with other spin numbers than 1 over 2. These particles include all the quarks, electrons, and neutrinos, and their heavier cousins. Okay. So guys, I think maybe the video is becoming long, and I cannot go on and on and on, because let me do the last one. Which nuclei have a half integral spin? If the number of neutrons, and the number of protons are both even, then the nuclei has no spin. Okay? If they are even, the nuclei will not have any spin. If the number of neutrons plus the number of protons is odd, then the nucleus has a half integer spin, i.e. 1 over 2, 3 over 2, and 5 over 2. So I think guys will stop there. It's enough for today. Sorry that I have to give you this heavy stuff. I thought you wanna go deep down, and this is what it means to go deep down, the quark lane. It's crazy, man. Yeah? It's a lot. So I think in the next video we go to what is half integer value, what does half integral mean, and we continue in this this journey. Sorry for giving you this heavy stuff, but for those who have done physics, they are enjoying. Sorry for those who have not done this stuff, but please follow my videos, then you'll be able to understand these things. So I'll end it here for today. I'm laughing because I know what you're gonna go through. If you have not ever had something like particle physics, this is really heavy stuff. And please like, share, and subscribe to my channel, and comment about these things. So, you're doing quarks, right? When you talk about quark, what is a quark? The fundamental unit of matter. I don't know what they should call it a unit. Actually, you know, I don't follow my videos when I just do them. But you are following, so you know what it is. So see you in the next one. Bye from me today. Bye. Like, share, and subscribe. This heavy thing is quite educative. Bye.